for the entire discipline of calculus. The occurrence of methods preceded principles, which is common sense for anyone who knows a little bit about the history of calculus. The principle of calculus is the logical system to answer why calculus method is effective. What is the correct way to reveal the calculus method, and how to reveal more calculus methods? The number point model in current mathematics cannot describe principles of calculus, leading to the failure of establishing a complete, rigorous and scientific system of principles of calculus. The fundamental difficulty in establishing principles of calculus, based on the current number figure model, is to deal with the Ox delta x in delta y over delta x equals f of x plus Ox delta x. If we leave out the Ox delta x, f of x can be written as the form of the differential quotient. However, the bridge between the integral and the differential, or the derivative, does not exist. If we keep Ox delta x, f of x cannot be written as the form of the differential quotient, and the integral in the Leibniz form is out of the question. By means of the limit, we can remove Ox delta x. However, f of x still cannot be written as the form of a differential quotient. So mathematicians, headed by Cauchy, roughly set up principles of calculus in non-scientific ways. Which was the source of all ridiculous things in the area of principles of calculus. In last section, we had know the definitions of differential, then we will introduce the criticism of the current principles system of the calculus. Let's begin with the mistakes of current principles of differentials and derivatives. As a general rule, for y equals fx, x is the reason, while y is the consequence. In the meantime, y is the reason of its consequence, x is the consequence of its reason. This kind of relation has neither beginning nor ending, which is the law of the world. Its reflection on mathematics is z equals ey, y equals fx, x equals gt. Therefore, unless x equals t, we should admit delta x is not equal to dx because of the formula 1. Someone may say that x is the original variable, thus x equals t always stands up, so dx equals delta x. We may ask, if this argument made sense, what we could say about the derivatives of the implicit functions, what we could say about the derivatives of the parametric equations, and what we could say about the second substitute method for indefinite integrals. What we discussed above is the situation of one variable. It's more ridiculous when we turn to the calculus of functions of multivariables. Set a function of m variables fx equals fx1 until fxm, which is defined on a neighborhood of the point x0 equals x01 until x0m. If there exists ai in R, I goes from 1 to m, for delta x equals delta x1 until delta xm sufficiently small. We have formula 2. Then we can say that function f is differentiable at the point x0, and we name this as the total differential at x0, which can be marked by formula 3, when we make the convention formula 4. In fact, if we replace each variable xi with a differentiable function xi equals xit where t from t1 to tk, I goes from 1 to m, therefore, according to the chain rule for computing the derivative of composite functions, we have formula 5. Thus, it is ridiculous to define delta xi equals dxi forcibly, or make the convention of the same thing. If we expect to make a deduction in Cauchy's style, we have to stipulate x equals xi, where I goes from 1 to m. Thus x1, x2 until xm all equal x can be deduced. However, in this way, functions of multivariables will degenerate into functions of one variable, which is absurd. In a word, the premise of current principles of calculus is that the increment of the independent variable of a derivative itself is always equal to the linear part of this increment, regardless of whether the increment grows according to linear or nonlinear relationship. Is this premise reliable?